So let us start with today's question. So today's question is a four-stroke SI engine has a compression ratio of 9:1 and operates with an air-fuel ratio of 15:1. So let us write the given data of question itself. So that is given is the first step is of the solution will be the writing of the given data that will help you in solving the question. The compression ratio that is we indicate as R is given as 9:1, air fuel ratio that is 15:1, and intake air temperature, intake air pressure. Intake air pressure is 1 bar, and intake air temperature 300 Kelvin. And in the question, it is given that the maximum cycle temperature is 1800 Kelvin, and it behaves as an ideal gas, and it 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 is telling us to assume as an air standard Otto cycle for the analysis. So we'll draw a Otto cycle here for better understanding. So let us draw the PV diagram of Otto cycle here. So let us draw here. This is the PV diagram. So here the constant pressure for heat addition, compression. So this is a rough diagram so that you can get an idea of what is happening in this question. So let us identify the points here. Point 4. I will identify the point 3 for understanding. That is the max from the question, as it is given that the maximum temperature is in the cycle is 1800 Kelvin. So what you can understand in the engine that when there is a maximum pressure is within the cylinder, at that point of maximum pressure there will also be a maximum temperature at that point. As the pressure increases, temperature also increases, as we have PV equal to RT relation, as the question is given that there is given that as the pressure increases, temperature should be also increases for the relation. Yes, as it is a constant volume heat addition, as pressure increases, temperature will also will increase here. So given that this two lines, 1 to 2 is compression by adiabatic compression, and 3 to 4 is expansion adiabatically. Okay, both are adiabatically. So what we have from the adiabatic relations here, it is given that adiabatic relation we have P1 comma equal to P2 comma. It is came from the equation PV to the power gamma equal to C, and we have another relation T1 V1 to the power gamma minus 1, T2 V2 to the power gamma minus 1. This relation also comes for this relation itself. And also there is given one significant thing that specificity is variable in this case. So specificity is given as the variable specificity given as in the question is 0.00025 T, that is it is given in kilojoule per kg Kelvin. Okay, so specifically it is varying according to the condition in the engine itself. So what we have to find out is the temperature here, the temperature and pressure at the end of compression. That is from the diagram you can see that the compression occurring end of compression occurring at point 2, and starting of the compression is point 1, as we have written in this line, as starting is 1.1 and the ending of the compression will be point 2. So in these 2 points we will apply these adiabatic conditions to find out the pressure and temperature at the end of compression. So we have P1 comma P2 V2 comma. At point 2 there is ending of the compression. So at point 2 we have to find out the pressure and temperature, as compression is completed at point 2. So from this, P2 is equal to P1 into V1 by V2 to the power gamma, and we have compression ratio is 9, which is equal to V1 by V2. From the diagram, we can identify that these points as V1 and V2 itself. Okay, these 2 points V1 and V2 itself, that is V1 by V2 is equal to compression ratio of the cylinder, and we will find out the P2 as P1 is given as intake pressure 1 bar into P1 by V2 is 9 to the power gamma is taken as 1.4 in this case. Gamma is taken as 1.4 in this case. So 1.4, this will give us 21.64 bar. So this is the pressure at the end of compression stroke. Okay, this is the pressure at the end of compression, and the temperature relation will be T1 P1 to the power gamma minus 1, T2 V2 to the power gamma minus 1. From this relation, T2 is equal to T1 into P1 by V2 to the power gamma minus 1. That is, T1 is given as 300 Kelvin into gamma is 9. Gamma means that is the compression ratio is 9 to the power gamma minus 1 is 1.4 minus 1. This will give us T2 is equal to 722 point, I think 46 Kelvin. So this is the temperature at the end of compression, as the point 2 indicates the compression end of compression in the Otto cycle diagram. As you can see, compression ends here. Then here constant volume heat addition takes place as at constant volume as V2 equal to V3. The constant volume heat addition takes place, and then the adiabatic expansion takes place. Then constant volume heat rejection also takes place here as P1 equal to P4. So you understand this. So by that thing, we have to find out the heat supplied per kg of air. So from relation we have heat supplied uh, on the conventional relation, we have at heat supplied at constant volume is equal to mcv delta T, as we have to find out for the variable specific heat, as it is indicating that in the question itself the specific heat is varying with a temperature itself. So for we have this point as we have this delta T for a delta T for a standard temperature, and for the particular temperature we have the temperature differences here, and for that we mostly take the Cv as constant for that, but in this question the Cv is changing with temperature, and we have to find out the heat supplied per kg of air. So we have to rewrite this equation as for dq heat supplied, there will be Cv dt, as this will indicate q is kilojoule, and that is mass is divided, so kilojoule per kg. So air daily heat supplied per kg of air according to the question. This should be the approach of the question itself. So by integrating this, we will get the total heat supplied. Okay. So integrating this from T2 to T3, Q dq supply is equal to integration T2 to T3 Cv dt. Why we taken T2 to T3? As you can see from the diagram itself that heat heat is increasing from temperature T2 to T3 as heat is supplied from point 2 to point 3. Understood? So let us write Cv here, T2 to T3, and here bracket 0.718 plus 0.000025 T dt. Simply integrating this, we'll get the answer here. So here we got here Q supplied 0.718 integration T2 T3 dt plus 0.000025 integration T2 T3 T dt. Simple integration takes place here 718 T, that is T2 T3 0.0000025 integration T square by 2, that is T2 T3. As it is a definite integration, so there will be no constants here. We have the T2 and T3 value. For that, first we write the simplified equation T3 minus T2 plus 0.0000025, that is divided by 2. This 2 comes here, then into uh, there will be T3 square minus T2 square. So T3 and T2 we have. For the maximum temperature of the cycle is T3, that is 1800 minus 722 46, that is found out from the above relation of the adiabatic compression, uh, plus 0.0000025 divided by 2, 1800 square, 722.46 square. From this we get 807.64 kilojoule per kg. So this amount of heat, is supplied per kg of dry, per kg of air. That is per kg of air, this amount of heat is supplied. 807.64 kilojoule of heat is supplied per kg of air. So now we have to find out the thermal efficiency. Okay, now we have to find out the thermal efficiency. For Otto cycle, we have the thermal efficiency formula as in terms of compression ratio. Uh, we have compression ratio is 9 to the power 1.4 minus 1. So from this we get thermal efficiency as 0.5846. In percentile it will be 58.46 percentile. So the thermal efficiency will be 58.46 percentile. By this we got all the values that is given in the question. I hope you understand the process of solving this kind of question from the diagram itself. By understanding the diagram and its the given data, the importance of given data is pretty much knowledgeable in this question, and you have to rethink while solving this type of question as it includes variable specific heat. So thank you for watching. If you got um, any solutions, any suggestions, you can give, and if you got any benefit from this video, you can like, share, subscribe. Thank you.